Hello, welcome to this third lecture of this module. This module we are discussing about multiple random variable, and so far in the last two lecture we have discussed about their joint probability distribution, and we also have seen in the last class that what is the marginal probability distribution. And in this class we will take up another concept which is also very important for this multivariate statistical analysis, which is known as the conditional probability distribution. So, this conditional probability distribution is generally can be obtained from the joint probability distribution, and its concept is very important to make it clear, so that its application will be easier for in different fields, including the different fields in civil engineering. So, our today's lecture will be on this conditional probability distribution, and as I told that this conditional probability distribution, and for all the multiple random variables, the concept when we are discussing, we will be discussing first for the two random variables, which will be easier to understand the concept, background concept. And after we learn that concept, and that concept can be extended for the higher number of random variables. So, and also one more thing that I want to tell at the first, that this when we are when we will be discussing this conditional probability today's lecture, we will first take up the that discrete random variable first, and from the discrete random variable we will then we will go to that continuous random variable. So, why the discrete random variable we will take first is that on the discrete random variable, that this concept will be, I feel it will be easier to understand. So, that with the help of some example, we will discuss that the discrete probability distribution first, and then we will use the same concept for the continuous random variable. So, our outline for today's lecture is this, that in this conditional probability distribution, first of all we will discuss in general what is this conditional probability distribution is, and how this can this is obtained in the general sense. And then first of all we will take this discrete bivariate random variable, this discrete it is, and also we will talk about these two random variables which is bivariate. And after that we will discuss about this continuous bivariate random variables. We will see the example problems as well, both for the discrete random variable as well as for the continuous random variable, and we will see that their usefulness of this conditional probability distribution concept. And then we will discuss about means it is not that separate, but simultaneously we will also learn the joint distribution versus conditional distribution, in the sense that how these two are related. Means what is, so we have in the last class we have discussed about the joint probability distribution, and in particular for the bivariate random variable we have seen that this can be shown in a pictorial form in a three dimensional space, in the sense on the paper we can show. And from that joint distribution, how we can get that conditional distribution, what this conditional distribution means. So, that we will discuss under this joint distribution versus conditional distribution. And another thing which comes from this conditional probability distribution is the independent random variables. This independent random variable means as the that language refers to, is that the two random variables which are independent to each other, that is outcome, or the two random experiment outcome of one is not influenced by the outcome of the other. So, that is the independent random variables, and from this conditional probability concept and the joint probability concept, we will also discuss mathematically what this independent random variable means. So, this is overall the brief outline that we will follow in today's lecture. So, first of all we will start with that conditional probability distribution. The conditional probability distribution is defined as the probability of some event x given the occurrence of some other event y. So, here we are discussing with respect to two random variables, one is that x and other one is y. So, what is supplied means that if we want to know the word, if we just want to take the word conditional. So, what is the condition to this is that the condition of the y, that is the occurrence of the other event y has already occurred and we know what has occurred for that random variable. So, that is the condition. So, once we give that condition is, so there will be some change of the distribution of the other random variable. So, what I want to mean is that we know the joint distribution if the x is this and y is this, means I am referring to some sets. So, x is in this set and y is in this set, and for the discrete random variable x is having a specific value and y is having a specific value, then their probability we know from the PMF, that probability mass function, means the joint probability mass function. Now, here the condition is that one variable I already know, suppose that y I know. So, the occurrence of the y, the outcome of the y is already known. Then if it is known, then what is the distribution of the other random variable, that is what we are referring to as the conditional probability distribution. This conditional probability distribution is expressed as this, that p x unconditioned y, and these are the variables, these are the specific value that this random variable can take, and this is the way we express that function, and this is read as the conditional probability of x given y. So, you can see that notation, that x slash y, that means the x given y. So, this is the way we express that conditional probability distribution. Now, you can recall that when we are talking about this joint probability distribution, we are referring to the simultaneous occurrence of both the random variables. We generally use the x and y both are occurring simultaneously. Here what is the difference with respect to the joint probability distribution is that this y has already occurred. What is the distribution of x? So, the distribution of x for a specific outcome of the y. So, this is the this is our interest when we are referring to the conditional probability distribution. Now, if we take off that discrete random variable and continuous random variable separately, then first of all, if we take that discrete bivariate random variable, that is two random variable x and y, and both are discrete random variable, and we have also shown in the last class how their PMF looks like in a tabular form, that is x are taking some values and y are taking some values, and for each of their intersections, suppose that x takes that value, some values say 1, 2, 3, 4, and y also can take those specific values. Then for each combination of these two, that probability mass is concentrated, and that is referring to the joint PMF. Now, from this one, if we want to know what is the conditional, then it is expressed like this. So, if the value of one variable, say the y. So, y we are taking that y, that means that y is the condition is fixed, that is y is equals to yi. So, yi is some specific value that has already occurred for the random variable y. Now, so this is we are using as a condition for the probability of x is equals to x, some specific value of that random variable x, that will now depend on the outcome of this y, that is yi here. So, we have the conditional mass function, conditional probability mass function as the p x unconditioned y, x unconditioned yi, that is y specific value is yi has occurred, which is also expressed as that x is equals to x and y is equals to yi, which is expressed as the probability of x equals to x intersection y equals to yi. So, here we have to know that when we are talking about this x is equals to x, that means whatever the possible values of x that can occur in with in concurrence of this y is equals to yi. Suppose that x can take the values of some set of values 1 to n, and y can also take the values from y 1 to n, but we are talking about for the y we are talking about one specific values, say y equals to 3. Now, for y equals to 3, now x equals to x means x starts from whatever the possible values that can occur when y is equals to 3. If the x can take all possible values for y equals to 3, then I should take those combination, that is y equals to 1 x equals to 1 y equals to 3 and x equals to 2 y equals to 3, x equals to 3 y equals to 3, x equals to 4 y equals to 3. That means I am not changing the y, that is y has already occurred, but what I am looking for is the all possible values that the x can take when the y is fixed for that particular outcome. So, these probabilities we will see, as well as what we will see, we will just this quantity is generally divided by probability of y equals to yi. Mathematically, it may be little difficult to start with that why we need to divide it this quantity by this amount, that is probability y equals to that specific value yi. In this case, that we are giving the example y equals to 3. That will be clear in a minute when we will discuss this thing with respect to the properties of the probability function. So, you know, this is also a probability function. So, those properties of the probability function that we discussed earlier should also be satisfied by this probability function. Now, when we are talking about that, then in a minute I will just come back to this, why we need to divide by this quantity will be clear. So, now this thing how we can express it again is that, so this is now what happens is the joint distribution for the specific value of y. So, this we can write that p x y, this is a joint distribution for x equals to general values x and y is a specific value yi, divided by, now when we are talking about the probability of y equals to yi, that means I am not giving any restriction for the x. That means what we discussed in the last class is that this is nothing but the marginal probability at y equals to yi. Now, how we get this marginal probability? You know that we have to sum up the quantities of this probability for all xi for the specific value yi. So, this is nothing but the marginal probability. So, that means this is the joint probability x y for the specific value y divided by that their marginal probability for all I. This will give that that conditional probability of x given y. This will be more clear when we are talking about in terms of some example. Basically, here when we are maybe the discussion when I was continuing, I was just referring to a specific value of y, and I specifically mentioned that this y equals to 3. But remember that it need not be the specific values only. What we are referring to a subset of the possible value of the y, that is on which it is conditioned on. So, it can be a range also. So, what I can say that the y greater than some specific value. So, condition is that y greater than 3. So, that is also a range. So, this also can be conditioned upon. We will just see in a minute through one example. Before that, if we just see that what are the properties, then the properties of conditional PMF, and you know that for a PMF the range of conditional probability is 0 to 1. That is, this is the conditional probability which is also a probability function. Either this is now this is we are talking about the probability mass function, but it can also be for the continuous case it will be the probability density function. And you know that these are this is always that between this is a positive number. So this is a non-negative number, so it can take from this 0, so it should be greater than 0, and I think so okay, this is a mistake, it can take any value. So the probability mass function, the value of the mass function or probability density function, whether it is a conditional probability or not, that is in general that this should be greater than 0. Now now as we are discussing this one with respect with the specific to that probability mass function, and we know that this cannot be more than 1, because the second properties is that summation of all these probabilities should be equals to 1. So this automatically implies that one individual value should be less than equals to 1, because their summing up should be equals to 1. So which is the second property of the probability function, probability mass function, also the probability density function. So for that conditional probability, that is x given y and y has a specific value yi, then for all possible xi, if we sum up the probabilities, that probability should be equals to 1. And we will just use this property to explain that why we need to divide it by this by the marginal distribution. This is the mathematical clarifications or why we need to divide it by their marginal probability. But conceptually, if you see, then this can be stated like this, that when we are talking about that this is condition on some outcome of the other random variable, here it is y, that means that has already occurred. So if we say that that has already occurred, that means I am now my irrespective of fine. So if we just draw this diagram, this will, I hope that this will be clear. Suppose that this is the two dimensional space that we are talking about. Now there are, for example, for the discrete random variable, there are some probability mass are concentrated at some specific points. Now when we are talking about that, it is conditioned on y, and y is having some specific value that we have decided that it is yi. That means I am already in this, so the outcome can never be on this zone. Outcome should be on this zone, on this line in this case, because it is a specific value we are talking about, or if it is a range, then on that range it will occur. So the entire probability that we are talking about, that their sum up, that condition, when I am talking about the conditional probability, that conditional probability, the entire thing, that sum up should be equals to 1. That is our requirement. So what we are talking, that this is that this has to be divided by its marginal density of this conditioned random variable to satisfy that properties, because we are already in this, we are already in this subset of the of this random variable. So this will be I hope this will be even more clearer to you when we are discussing with respect to a problem. One more thing here, that is under this note, that if we just see that this is the expression and this the marginal probability that we are talking about. Now if the marginal probability for some yi, if it is 0, then what will happen, because this is in the denominator. So here now from this picture also you can see that if the yi for this on this writing pad, if you say see that on this, if we are talking about some yi where the marginal probability is 0, that means that is not a feasible event for the y. So this might be, if this is the total space, if this is the total range or the support of this random variable, so that I am talking about some yi which is outside that range, or which is taking some set where there is no outcome, that means that marginal probability is 0. So, if the marginal probability is 0 itself, then there is no meaning of this the conditional probability. So, in that case the conditional probability will obviously be 0. So, this is what is written in this note, that conditional PMF is 0 when the denominator is 0, that means the marginal probability if it is 0. Now, let us take one example on which we will discuss these things of this we will discuss the concept of this the conditional PMF. So, we are taking the similar problem that we have taken earlier in the last class also, just to maintain the similarity on the same type of problem we are just taking to discuss their joint. We have discussed the marginal, and now we are going to discuss the conditional probability distribution. So, stream flows at two gauging station on two nearby tributaries are categorized into 4 different states, and we explained earlier that what are these states, means how we why we need to categorize into different states. Say that these states are named as this 1, 2, 3, 4. Maybe you can also say that this is the 1 is the low flow, 2 is the 1 is very low, 2 is low, 3 is high, and 4 is very high, kind of thing. So, this type of categorization what we are referring to here. So, these categories are expressed by two random variables x and y. So, you know the as I told earlier, of course, that the stream flows are generally the continuous random variable, but when we are doing the analysis with the categorized stream flow, that means these are discrete numbers. So, these are the discrete random variables. So, here the x and y, that is the states for these two nearby tributaries at two gauging stations, these x and y are the discrete random variable. So, the PMF of the stream flow categories x and y are shown in the table on the next slide. This we have also shown in the context of the other concept in the earlier lectures. Now, here what we are supposed to know is the estimate the conditional PMF of x given the condition as y is equals to 2. Now, what we discuss before I go to the solution, what we discussed so far for the conditional distribution is that here you see that the when we are not telling anything about y or anything about x, what we are having is their joint PMF, that joint probability mass function what is available to us. So, we know for a specific combination of x and y, that is if x equals to 1 and y equals to 2, or some other if x equals to 3 and y equals to 1. So, for such cases what are the probabilities that we know from this joint probability mass function. Now, here the for the conditional PMF we are saying that the y is equals to 2. That means, suppose that this type of situation when it can happen is that suppose the one tributary is accessible and otherwise is not for some rare reason. Now, if we have the first record, if we know their joint distribution, now if we are if we know that what is the status of the stream flow for one station, so that means I know the status of the one station which is in category 2, then I have to conclude that what could be the possible state for the other station. So, this is you can just think of this real life situation where this conditional PMF, for this case I am talking about this case, that can be applicable. So, here we have to estimate the conditional PMF of x given that y is equals to 2. So, let us first see about that PMF. So, this is given in a tabular form, and this 4 by 4, if we just see this 4 by 4 matrix, then this is actually giving this entire joint PMF, that is 0.31. This is nothing but the probability concentrated probability for the case x equals to 1 and y equals to 1. Similarly, the 0.025 is the probability in case x equals to 3 and y equals to 2. So, this is the joint PMF, and we have also seen that if we just add this up, that is 0.31, 0.06, 0.00, 0.00, then this means what? This is x equals to 1 for all possible values of y, that means the irrespective of the values of y. So, if we sum it up, then this is nothing but the marginal probability of x, marginal probability of x that we discussed in this last class, that is irrespective of the value of y. So, this the last column what is shown is that the marginal distribution of x, that is this is 0.37 is the probability of x equals to 1, 0.41 is the probability of x equals to 2, 0.17 is probability of x equals to 3, and so on. Similarly, for the y also, the marginal distribution we can get for a specific value. If we add for all different possibilities of x, then for example this 0.37, then this is the marginal probability of y when y is equals to 1. Similarly, 0.446 is for the y equals to 2, and so on. So, this is the entire description of this joint PMF and marginal marginal probability distribution that we discussed in the last two classes. Now, what here the new thing that we are talking about is that it is conditioned on that y equals to 2. So, as we are conditioned on y equals to 2, then that means that now our concentration is entirely on this column, entirely on this column. What we are meaning is that the for a specific subset of y, now we are talking about the whatever the distribution for the x for this case only. So, that is this case means here it is y is equals to 2. So, in the next slide towards the solution of this thing. So, this is the joint probability values, that is what we have seen for this different combination of x and y, and y is equals to 2 here, that we are talking about the 0.06, 0.036, 0.025, 0.001. What we are just picking up this column actually 0.06, 0.036, 0.025, 0.001, which is for x equals to 1, x equals to 2, 3, 4 respectively. Here also we are taking that. This should be 1, this is a typing mistake. So, this x equals to 1, this is x equals to 2, this is x equals to 3, and this is x equals to 4. So, we are simply taking that column, that is for that set where y is equals to 2. Now, you know, if we just add it up, then what we will get? We will get the marginal probability of y for y equals to 2, which is that 0.446, which we have also seen in this earlier slide, that for y equals to 2, this summation is 0.446. So, this is the summation that we get. Now, if we see that this conditional probability function, that is conditional probability distribution, which is equals to their joint distribution divided by their marginal distribution, that is 0.06 divided by this one will give you these values, and similarly 0.36 divided by 0.446 will give you this, and similarly it will give. Now, you see that what we are talking about, this y equals to 2 is giving this specific value. Now, this one, the first thing is now clear, as we are just making this division, that is 0.06 by this one, we are getting all non-negative numbers. This is the distribution of x with condition that y is equals to 2. Now, as we are dividing it by these values of to this marginal with their sum, basically we are dividing it with respect to its sum. So, then the summation of these probabilities will be 1. So, if we add this 0.1345 plus 0.8072 and these things, we will get that this is equals to 1, which is again the second condition for that joint PMF of that bivariate PMF, that conditional probability function. So, this we have seen. So, here you can now see that mathematically the summation is equals to 1, and this is because that we are dividing it by their marginal probability, and why we are dividing it with this one, because as we are, the condition is y equals to 2, that means we are definitely for in this column. So the occurrence of y equals to 2 we have make sure, because that is our condition. So that is why in this entire, in this set itself, that is set means here that y equals to 2, the summation of the probability should be equals to 1, because this is a definite case. So for y equals to 2, it should be either x equals to 1 or x equals to 2 or x equals to 3 or x equals to 4, because there is no other possibilities. So now that is reflected in this concept. Now again we will just take that for a specific range. So earlier what we have talked about this specific value of this y. Now if we just want to see that for the range, the keeping the same concept background, this can be expressed as the probability distribution of x when y is not less than some specific value y, that means y greater than equals to this specific value. So this conditional probability mass function is given us. So probability x on condition y, the y is now a range, that is y greater than equals to that specific value y. So probability x equals to x on condition y greater than equal to y. So which is equals to this what now we are taking this joint probability distribution is that for that range, for y greater than that specific value, what is the probabilities for different values of x. So that we are concentrating on the specific range of this specific range of the joint PMF. Okay. Now similarly for the y, when we are taking this marginal distribution, that marginal distribution is for the specific range. So again we are taking up that same problem, and here the question is that estimate the conditional probability when y is greater than equals to 2. So instead of giving a specific value, we are giving a range. So again this is a joint probability mass function, and these are the marginals. What we are referring here is that y greater than 2, that means we are referring to y equals to 2, y equals to 3 and y equals to 4. So this range, so I have to exclude this case, that is y equals to 1. So y greater than equals to 2, for this case the entire PMF part we will take, and we will also take what is the marginal distribution for y when y is greater than equal to 2. So y is greater than equal to 2 means I have to take the take these probabilities only. So 0.446, 0.134 and 0.050. So if we just see the same thing here, that is for this so this one, when we are taking these three, that marginal probability for this y greater than equal to 2, sorry, this is y greater than equal to 2, then 0.446, 0.134 and 0.055 we have added up, and we got that 0.63. So once we get this one, so this is our marginal probability for random variable y for the range y greater than equal to 2. This will be 2. Now the conditional probability of x with known y greater than 2 are these values. How we are getting these values is that when x equals to 1, for all values which are greater than, for all values of y which are greater than equal to 2, that means if we refer to this joint PMF, that is x equals to 1, all values which are greater than equal to 2, that means 0.06, 0.0, 0.0, this summation is 0.06. So that means we are taking 0.06 for x equals to 1. Similarly, for x equals to 2 and y greater than equal to 2, we have to add up 0.36 plus 0.01 plus 0.0, which is 0.37. So we are just taking that 0.37. Similarly, for x equals to 3 and x equals to 4, we can get. Now these are the probabilities, and this is the marginal probability for that range of y. So, next to get their conditional PMF, we have to take this 0.06 divided by 0.36 for x equals to 1. Similarly, for x equals to 2, 0.37 divided by 0.63, and similarly for x equals to 3 and x equals to 4. This is what is done here, that the conditional probability of x when x is not less than 2 is this. So, these values that we have discussed and this one that we got. So, if we just divide these two numbers, then for that x equals to 1, the probability is 0.0952, for x equals to 2, 0.58773, for x equals to 3, 0.2683, and for x equals to 4, 0.0349. So, if we add up these probabilities, it will be equals to 1, of course. So, now if this one is taken, that now as I at the starting we was just mentioning that how we can relate it for the conditional to the joint, then mathematically the relationship from that form, it looks like this, that is joint PMF can also be computed using the conditional PMF and the corresponding marginal PMF. So, that means from this equation actually. So, from this equation, this is the joint and this is the marginal. So, the marginal multiplied by this conditional distribution will give you the joint. So, that one, so joint distribution is equal to this is the marginal distribution and this is the this is the conditional distribution and this is the marginal distribution. So, if we just take these two, if we multiply these two, obviously this will be equal to its joint PMF. Similarly, so this says that this x on condition y multiplied by the marginal of y, this can also be expressed that y condition on x multiplied by marginal of x. So, both these things are same and is equal to its joint distribution. So, if we take one problem related to this, this is related to sometimes what happens for this orbiting satellite around the earth. We take the satellite imagery, and from that imagery we want to know any specific attribute of this land use land cover on the earth. Okay, so this generally help us to for different studies, different change studies. If we want to make some, what we do, we generally take the satellite imagery in an year, and after some year we take another one. So, two satellite imageries are kept for some year apart, and we see the change. For example, that deforestation. So, for 10 years how much forest area has decreased, or another application is also that we want to know that flood affected area. So, if we want to see it from the satellite, then I have to see that how much area is flooded. So, when the satellite observe the earth from the space, it looks in terms of the pixels. This pixels means is a small representative area which is taken as one unit to the sensor on board in the satellite. So, so these pixels, depending on the quality of the sensor, this pixel size varies. Now, one pixel size is known, is representing how much area. So, now if we know that what is the area of one pixel, now depending on the number of pixels for that attribute, whether it is a forest cover area or the flood affected area, we know that how much area is under that attribute. Okay. Now, sometimes what happens, this sensors, whether it will successfully detect a particular pixel for that attribute or not, that is a that we can express in terms of the probability. So, so here if I want to look into it in the concept of the conditional probability, here the condition says that the suppose that the example that we will discuss now is on the forest cover area. Suppose that a particular pixel is really having the forest cover area. Now, this is the condition that the pixel is really having the forest cover area. Now from the satellite when you are looking, now the question is whether that satellite can say that whether yes it is forest cover area or no. So obviously the good sensors will have the probability of success should be very high, and the defective sensors may not be that high. So this is also a chance. So the condition on the real ground truth, so whether what is really existing on the ground, that is the ground truth that we refer to. So the condition on the ground truth, what is the outcome from the sensor, that we will see through this problem that we are discussing now in the light of the conditional probability distribution. A satellite borne sensor is used to determine the area of land cover change after some period of time by detecting the number of pixels reflecting forest cover. This sensor has a chance in percent of 100 pi to successfully detect a pixel having forest cover or not. Thus, the conditional PMF that M2 pixels are detected when M1 pixels are actually covered by forest area is given by the binomial distribution as follows. So now that the chance that we are talking about this 100 pi, this is the probability that whether a pixel will be successfully detected or not. So if the ground on ground really it is the forest cover area, what is the probability that that will be truly detected by the sensor, that is given by this probability. Now suppose that there are total M1 pixels are there, M1 pixels means M1's equivalent to that M1 pixel area are actually forest cover, and the sensor has detected M2 pixels, that means M2 is less than M1. So depending on their probability of success that we have discussed in the previous module also, you know, this will fit as a binomial distribution. So this binomial distribution, now there are two random variables here, one is that M1 and other one is the M2. So probability of M2 on condition M1, these are the variables on which we are representing M2 M1 is equals to following that binomial distribution, that is M1 C M2, that is M1 combination M2, that probability of success power, how many pixels are successfully detected, and this is 1 minus pi probability of failure, that power how many pixels are not actually detected, that is M1 minus M2. So this is the conditional distribution of M2 given M1. Now for that M1, so how many pixels are there actually covered by the forest, that is now so that is basically when we are considering that how many pixels is forest cover area for a given area, that is now irrespective of how many will be detected. So that means this is equivalent to the marginal distribution, and this marginal distribution is having is assumed to have a Poisson distribution. So here the parameters of this Poisson distribution is lambda, and it says that it is assumed that the distribution of M1, that is the number of pixels having the forest area, actually having the forest area, is given by the Poisson distribution, which is expressed as this, that lambda power M1 e power minus lambda divided by factorial M1. So we have to find the joint probability distribution function of M1 and M2. This is straightforward that we have seen in this last discussion, last slide, that how to get the joint distribution once the conditional and the marginal is available to us. Also, if delta A is the unit area of each pixel, that just now I explained that each pixel depending on the sensor capacity it should refer to some actual area on ground that is represented by one pixel. So here it is that delta A. So delta A is the unit area of each pixel. Determine the probability that an area covered by forest cover A larger than k delta A remains undetected by the sensor. So basically what we are looking for is the difference between that M1 and M2. M1 is actually forest cover, M2 has been detected. Now, when we are talking about that, 1 unit pixel is having the area of delta A, and we are talking the total area undetected is capital A, and which is equals to the k delta A. That means, we are talking about the difference is equals to k, that is M1 minus M2 is equals to k. That means, the total area will be k delta A. I repeat the question once again here. The second one is that if delta A is the unit area of each pixel, determine the probability that an area covered by the forest cover A larger than k delta A remains undetected by the sensor. So, to solve this problem, first that to get that joint distribution, we will see that joint probability that there are m pixels of forest cover, and that M2 of these pixels are detected by the sensor is given by that probability M2 comma M1. This is we are talking about this joint distribution, which is equals to, as we discussed, that this is a conditional distribution, that is conditional distribution of M2 given M1 multiplied with the marginal of M1. So, both these informations are available to us. So, we will just multiply them to get their joint distribution, which is lambda power M1 multiplied by e power minus lambda divided by M1 factorial multiplied by this is this expression is basically M1 combination M2. So, M1 factorial divided by M1 minus M2 factorial multiplied by M2 factorial multiplied by pi, that is the successfully detected, the probability of success, power M2 multiplied by 1 minus pi power M1 minus M2, and which we can, after some simplification, it comes to this form. So, which is the joint distribution of M1 and M2. Now, the second question, which is interesting, is this, that the probability that an forest area A larger than k delta A remains undetected by the sensor is given by, that means, we are looking that probability that A greater than k delta A. So, A greater than k delta A, as we have explained, that is this delta A is the area for one pixel. So, that means, this is there are k pixels are there which are undetected. Now, the undetected pixel in terms of the random variable that we are discussing is M1 and M2. So, M1 is the total number of actual pixel which is having the forest cover area, and M2 is detected. So, M1 minus M2 greater than k. This is, so these two probabilities, that is that we are referring to, and that is the M1 minus M2 is greater than k. So, we have to find out this probability from the joint distribution. Now, from this step to this one, how to get this this expression, that we have to, it is simple, that in terms of the, if it is continuous, then it is, we will have a joint integration, or if as it is a discrete, then we have to go to a summation, but summation we have to do with care, that which area that we are referring to. Note one thing here, that this is greater than k that we are talking about, that equality sign is not there, because we are interested to know that greater than that particular value. So, how if we just want to represent it in terms of a pictorial view, just to know that what are the limits that we get for this summation, is this. Suppose that this is your M1 and this is your M2. Suppose that this is your M1 and this is your M2, then there are some so obviously there, this is a discrete probability function, then we can have a different values of M2, and one satellite imagery generally have many numbers of such pixels. So, effectively you can say that these are many possible values on this M2 and many for this M1. And of course, but one thing is true from the distribution also, from the Poisson distribution as well as the binomial distribution, you know their support by now, and all is starts from 0 to infinity. So, it takes in this zone. So, maybe the 0, 1, 2, 3, 4 it can take in this zone. So, the area that we are talking about, this is starting from 0 and goes the infinity towards this, and from 0 goes to infinity towards this, taking some specific values. Now, what we are talking about is that m1 minus m2 is greater than k, that is what we are referring to. So, which area is referring to this inequality is that, suppose that this is your k, that is m1 equals to k. So, if I draw a line passing through this k and having an angle 45 degree with the m1 axis, that means this m1 minus m2 greater than k refers to this zone, but excluding this line. If it is equality sign comes here, then including this line, but as we are talking about that this zone is greater than k, that means this is the area that we are talking about, is this zone is that area of this inequality. Now, what we can do is that if we want to know what is this area excluding this line, there are two things. One is that I can get the summation for this full area, and I can get the I can get it, or as it is there, as this line is included, we can do the other side also. We can do the summation for this area, and that we can take from this 1 minus of this one, because we know the summation of this full thing is this 1. Okay. Now, suppose there are some the probability mass is concentrated for this specific combination of m1 and m2, and suppose that these are the that contours of the probability of the joint probability. Now, basically what we are doing is that if this is obviously this is a discrete random variable that we are talking about, but you can also imagine that this probability, this is just like a surface, and the surface is represented by the contours, and this contours we just want to know the part of the contour to get this probability of m1 minus m2 greater than k. So, which we have just replaced, as we told, which we have told in this way, that this one is equals to 1 minus probability of that m1 minus m2 less than equal to k that we are talking about. That means, we are interested to know this area in this and then minus it from 1. Now, to know this area, what should we do? If we just take a say that small strip, if we just take, then the range of m1 for this one. So, this is your m1 is equals to 0, and this point is your m1 is equals to m2 plus k from simple geometry. Now, so this strip that we have to sum it up, and we have to move this strip starting from 0, that is your m2 is equals to 0 here, and it can go up to that m2 is equals to infinity. Then we will get this total area. So, m1 ranges from 0, m1 equals to 0 to m2 plus k, then the summation is m2 equals to 0 to m2 equals to infinity. So, to know this area, then we will deduct it from the 1 to get what is this probability. This is exactly is done here. You can see now this 1 minus this 2 summation for this the joint distribution, and this joint distribution for this m1, first we are adding up the m1 equals to 0 to m2 plus k, and this one again we are summing up from m2 equals to 0 to the infinity. This probability is giving the probability m1 minus m2 less than equals to k, which we are subtracting from the total probability 1 to get this probability. Now, so this is the solution in the sense, if we know this parameter of those distributions and those thing, then obviously we will get what is the actual probability of the area to be remain undetected. So, in the so I'll stop for this class here, and what we will discuss in the next class is that how we will take this concept to the continuous random variable, how we will deal that the independence also, that in the light of this conditional distribution, that we will take in the next class. Thank you.